เบอร์กาโดนะครับอาจารย์เบอร์กาโดเนี่ยนะครับนะฮะไม่ใช่เป็นแค่ผู้เชี่ยวชาญด้าน Ground Improvement นะครับแต่เป็นผู้เชี่ยวชาญด้าน Ground Improvement ระดับโลกนะครับนะฮะจริงๆแล้วท่านคิดค้นนะฮะเทคนิคทางด้าน Ground Improvement ใหม่ๆหลายเรื่องเลยนะครับนะฮะไม่ว่าจะเป็นการใช้ PVD นะร่วมกับการทำ Thermal Consolidation อย่างนี้เป็นต้นนะฮะการพัฒนาเรื่องของการใช้ PVD นะในการปรับปรุงดินเหนียวอ่อนในสุวรรณภูมินะครับอาจารย์เบอร์กาโดก็เป็นคนทำวิจัยนะครับแล้วก็พัฒนาพารามิเตอร์ต่างๆนะครับตัวแปรหลายๆตัวที่เราใช้ในการดีไซน์เนี่ยก็มาจากงานวิจัยของอาจารย์เบอร์กาโดกับลูกศิษย์นะครับนะฮะแล้วก็ด้าน VCM เนี่ยด้าน Vacuum Consolidation เนี่ยนะครับท่านก็เป็นท่านแรกนะครับที่มาทำการวิจัยที่สนามบินสุวรรณภูมินะครับนะฮะแล้วก็ตอนนั้นเองผมก็ช่วยอาจารย์อยู่นะครับผมเป็นลูกศิษย์อาจารย์นะครับแล้วก็ได้เรียนรู้นะครับเกี่ยวกับเรื่อง VCM นะฮะในช่วงที่หลังจากจบการศึกษาแล้วนะฮะก็ทำงานกับอาจารย์อยู่นะครับนั้นเราโชคดีมากนะครับนะฮะที่ได้อาจารย์เบอร์กาโดมานะครับอาจารย์ก็จะมาเล่านะเกี่ยวกับเรื่องคอนเซปต์ทฤษฎีนะฮะภูมิหลังนะครับของ VCM Professor Bergado, I already introduced you in short that you are the world famous geotechnical engineer, especially in the ground improvement. You have been doing research and then many parameters that we use for the design actually came from your research and your practice. And you are the first researcher that perform VCM research in Thailand, which long time ago when I just graduated and helped you as a lab supervisor in AIT at that time in Suvarnabhumi airfield, ground field at that time. And I think participant is very lucky today to have you giving a presentation. During the presentation, I asked the participant if they have any question, they can type the question in the chat box, and after the presentation, I will read all the question and ask you after the presentation. Okay, now I turn the floor to Professor Bergado. You have 50 minutes for your valuable presentation. Thank you very much. Please turn on the microphone.
Thank you very much for, can you hear me now?
Yes, I can hear you.
Thank you very much for your invitation. And I'm quite delighted to join this seminar, and I'm quite lucky that when I was at AIT, this technique just came up, and there was nothing in a bank of clay, and was able to start the research, and I was able to succeed to do it in a subsiding ground. So today, my topic is about vacuum PVD improvement, concepts, and some application. I have been in this area since my work at the AIT for more than 30 years. And now I already retired, but I'm still a professor emeritus at AIT. So here at the screen left is my pioneering book in soft ground improvement that was published in 1996. And this is the first book that published all the ground improvement, soil improvement, and with geosynthetics. And in the right side is the first page of my Google Scholar. If you type my name, at the Google Scholar, you see all my publications. So when we improve a soft clay or soft ground, the clay has mostly voids. The solid is only around 40%, but the voids is full of water because it is below the groundwater level. So the only way to reduce the voids is to take out water, and it's called dewatering. So the previous work before is just for preloading by embankment surcharge. And this takes a long time because of the length of the drainage paths of the pore water to go. So the installation of the PVD or free fabricated vertical drain reduce the drainage paths to be only halfway of the spacing and makes the consolidation faster. So, but when the conventional way was to install the PVDs, put the surcharge fill, but since the ground is soft, you need a berm to prevent sliding or slope failure. But if you provide that without drain, it takes quite a long time to complete consolidation, but with vertical drain, it is faster. But with vacuum, it is much more faster by about 30% or even 50%. So the PVD are artificial drainage paths made of geosynthetics composed of the core, which are channels of flow that conduct water up through the drain vertically, and a filter jacket is to minimize, it is around the core, minimize the entry of clay particles, but allow water to pass through. So this is installed as a square and triangular pattern by a modified backhoe like this one. But during installation, it caused disturbance around the PVD, and this is called the zone of disturbance or the smear zone. This is a barrier of flow because the key H is the original permeability. This is higher than the vertical permeability, but the key S, disturbed permeability disturbed zone, is quite low. It reduced by the disturbance. And most of the research was to look at how to mitigate this barrier of flow smear zone. And by using vacuum pressure, it mitigates this. And although I also have the research using electro-osmosis and heat or thermo PVD. But for using vacuum PVD, we are mitigating the effect of the smear zone. So by using vacuum, we are, instead of increasing the total surcharge, total pressure, that because the surcharge causes some slope failure, we are looking at reducing the pore pressure by vacuum, and the effect is the same. You increase the effective stresses. So in the left side here is a PVD consolidation. We only add the surcharge, and the hydraulic gradient cause the water to flow to the PVD. But the vacuum PVD, we apply additional atmospheric pressure, which is like an isotropic compression. The pressure is the same from all directions, horizontal, vertical. due to the atmospheric pressure up to 100 kPa, but we cannot go to 100 kPa, about 90 kPa we can add. So this is the schematic diagram. When we are applying the atmospheric pressure, it has effect on the pore water. So what is the benefits? Well, in cases where you need a lot of preloading, up to 90 kPa, we need to use surcharge and vacuum together, combining surcharge, embankment, and vacuum. But after vacuum consolidation, anyway, there is some settlements, and the embankment will compensate for the settlements. And lateral deformation due to embankment is outward, while using vacuum, it is inward. So there is some balance between inward lateral displacement and outward lateral displacement due to the embankment. That's why combining embankment and vacuum is ideal. This is the list of my publication involving vacuum PVD since 2009. And I look at it until last year, where we look at the microstructures within the smear zone. And all these things here prove that by using vacuum PVD, the permeability in the smear zone increase, and Ks over Ks reduce, because Ks, which is the permeability in this storage zone, increases due to vacuum. And we look at the macrostructures, the flocculated, the microstructure change from dispersed to flocculated, that increases the permeability in the smear zone. So the ground deformation here by vacuum, I use the paper of Professor Chai in 2005, published at ASCE, and he did this illustration that we have the soil with vertical and horizontal pressure. Horizontal pressure is K0 times the vertical stress. When we apply vacuum vertical and horizontal, and depending on whether the vacuum is higher than the overburden pressure, then you can have different some movement or different lateral displacement. And K also is a ratio between the vacuum pressure and vertical and the horizontal pressure, which is the sum vacuum pressure and the original K0 times sigma V0, the original from the unloaded soil caused by the overburden pressure. So when the vacuum pressure is higher than the overburden pressure, we have inward movement that cause some tension cracks. And this deformation can be predicted by the equations that provided by Professor Chai, as you can see here. And this can be used to check on the lateral movement. And this is the lateral displacement here at the bottom here, where B is half width of the area treated by vacuum consolidation. There was some case study in China This is the soil profile. And we compare measured versus observed values. And you can see the actual measured here is inward movement in the solid circular or triangular symbol, and predicted in the line. And you can see the prediction is almost agree with the observed inward movement. Another one, site in China, and you can see here use beta is an empirical factor, and here is soil profile and calculated and measured, observed and calculated. And you can see also that it is predicting the inward movement. So the idea is to combine vacuum with embankment preloading, another paper by Professor Tsai, published at the Canadian Geotechnical Journal. Shows the optimum penetration depth of the PBD when you don't have to go into the sand layer down below, because it will cause some complications. So you can stop it here, and you have some optimum length here, H1, which depends on the permeability of KB1 and KB2. And he also have, when you have two layers, he has derived equivalent vertical permeability when you have PBD. Then this is one-dimensional flow vertically, with KB1 is the equivalent permeability as a function of the spacing, and here the smear this is the vertical flow, smear and well resistance, including here with the spacing. So in Saga, there is the soil profile and the parameters, and use it to simulate if the vacuum is intermittent, reduce and then come back, because you reduce it and back. And then you have the settlements measured versus observed, and the lateral movement, which is inward movement. Then it proceed to do a numerical experiment. When you have the embankment already there, case 1, then you add intermittent vacuum. Case 2 is you only have the embankment load, surcharge load. Case 3, you have the embankment load but low. The height is low. Then you add vacuum. Then you increase the height of the embankment. This is case 3. You see the case 1 produce the maximum settlement because you have embankment plus vacuum. Case 2, embankment only, have this settlement mostly the same as case 3, which you have low embankment with vacuum and add the height of the embankment. Case 2 and case 3 almost the same settlements, but the lateral movement, case 2, embankment only has the largest outward movement, and followed by the case 1 here, but case 3, where you have low embankment and apply vacuum, you have inward movement because of vacuum is higher than the surcharge. And after 6 months, they all move outward, but case 3 here has the lowest outward movement, while case 3, only embankment, has the largest outward movement. The first vacuum that was used at Suvarnabhumi Airport, at this time, this was done by C2 with a direct connection. This we did not use now, but this is a direct connection of the pipes to the PBDs. And this is the soil profile at Suvarnabhumi. And so when you use conventional PBDs that we have done in our project at Suvarnabhumi, PBD only, and we need to have surcharge embankment of 4.2 meters high. And this we use a berm to prevent slow failure. But when you use vacuum, you have only about 2 meters high, 2.7 meters high, then apply vacuum. There's no problem with slope failure. Then the vacuum pressure at the embankment is around 90, and the vacuum pressure at this soil layer, underlying soil clay layer, is around 60 kPa. And this is the settlement. Compare PBD only and vacuum. And you can see vacuum is around 30% faster than PBD only, or 1.5 times higher rate of consolidation. Then at EIT, when I did my sabbatical in Japan, we have this model test, large scale model test, and we can put vacuum here with reconstituted clay, and we can put PBD only or with vacuum, and you can see here PBD only and called normal PBD. If you compare with vacuum, you can see vacuum, it's faster. That was our first experiment at the EIT. Then Dr. Sompo has at KMUTT has this kind of big equipment that simulate vacuum and PBD only. So vacuum PBD and PBD only. And my student also use this one. And you can see the photo of that big equipment at KMUTT. And this is the result when we publish this one. See the PBD compared with vacuum. You can see the PBD only 1.5 Ks/Ks, vacuum 1.45 lower, but the CS value is increased. So you have increased CS, did reduce Ks/Ks. By the way, Ks/Ks and CS are a pair, and they should be there all the time. And it Ks/Ks control the CS value or the coefficient of horizontal consolidation. Then we followed up with 3 simultaneous tests using PBD only, PBD with vacuum, and PBD with heat or thermo PBD. And we have measured the increase of shear strength at the smear zone. And you can see here the PBD only, then vacuum PBD, higher shear strength, then thermo PBD, highest. Thermo vacuum PBD is also the most highest. And the settlement here, PBD only, then vacuum PBD, then below here is the thermo PBD. So you can see consistently that with vacuum PBD, the settlement, the rate of settlement, and the time to consolidation is reduced. And you can see here, we measure by scanning electron microscope, the micrographs of here in the left side is the reconstituted clay, and in the right side is the after vacuum PVD. You can see that from the floculated after vacuum, the structure now is flocculated, while before vacuum is dispersed. And flocculated means stronger, higher strength, and higher permeability. These samples were taken from the smear zone. Then from the direct connection, the vacuum system progress by using airtight membrane and direct connection still with the PVDs to the vacuum pump. And this is much better to prevent vacuum leakage. And now our present project at the Sonapom Airport by the C2, you can see the air-water separation system is distributed in the field. And you can see connection of the vertical drain with the horizontal drain and the perforated pipes connecting to the vacuum pump. You see the distributed air-water separator, and this all connected to the vacuum. And then you can see that we use a lot of geosynthetics here. Separator, airtight sheets, which is HDPE or geomembrane, and geotextiles, horizontal PVD with vertical, and connection with the perforated pipes. This is the air-water separation with vacuum meter and water discharge during operation of vacuum PVD preloading. And the last portion of my lecture, we talk about the latest project we had located near the Sonapom Airport. And this is the borehole locations and field vane test location after the improvement. And you see the installation of the PVD connection with horizontal drain, connection with the perforated pipes that done by C2. This is a soil profile. That in that area, the depth of the PVD goes to around 17 meters. There was some 2 to 3 meters of surcharge that was there existing. Then we apply vacuum, triangular spacing, 0.9 meter spacing. This is designed by Francisco, and you can see 4 piezometers here, single and double piezometers. We have settlement plates and inclinometers for our monitoring instruments. You can see the 4 vacuum pressures go around 80 kPa, and we have 4 pressure in the middle of the clay around 60 single and double piezometers. So 80 at the top and 60 at the underlying layer, you can see it. But it reduced with depth according to that measurements also. Professor Chai, they reduced from around 60 to around 50 with depth. Then we have the settlements, and we divide these into zones 1 to 6, and we have the settlements, and then we have the rate of settlements in millimeter per day, and 90% degree of consolidation, or rate of settlements 5 millimeter per day, the criteria to stop the vacuum. You can say settlements from around 1.6 to around 1.8 for a thickness of 17 meters. So you can see the vertical compression is around 10% of the thickness of the clay. This is the general estimate of the compression of the clay. Using Asauka method, we can predict ultimate settlements zone 1 around 1.6, zone 3 around 1.8, 1.7, and zone 6 around 1.8 meters thickness settlements. Then when you back calculate Ks over Ks, ds over dm, and Ch zone 2 and zone 6, for example. At the Sonopom airport with PPD only, we use Ks over Ks around 5. But if you have the vacuum, maybe it will reduce to around 4, because it will reduce a little bit. And you can see that CS value around 3. Oh, that is used, that was used in the design. This is a diagram of before and after soil properties. Of course, the water content reduce, liquid limit reduce, the shear strength increase, compression index, compression, recompression, compression index reduce, void ratio reduce because we are compressing. So water content and void ratio reduce. But over consolidation increase and the maximum pass pressure increase from around 40 to about 80. The undrained strength increased by almost twice, from about 10 kPa to around 20 kPa, improving the very soft to soft clay to becomes soft clay or even medium clay. You can see here the field bend shear test, and before and after you see the increase almost twice, more than twice for very soft to soft, especially at the very soft to soft clay layer. Of course, there is cracking because there is inward movement. You can see the inward movement here, cracking around 6 meters from the edge of the loading area. So cracking did not disturb, did not affect the airtight membranes. So it did not affect the leakage. There was no leakage caused by cracking. Cracking around 6 meters from the edge of the loading area. And from the finite element simulation, you can see 6 meters from the edge, and the depth of the cracks around 4.2 meters. This one can be measured from the method of Chai 2005. So we have this simulation from finite elements for the distance of the crack and the depth of the crack. Then we look at secondary compression. The coefficient C alpha for recompression ratio of 0.05. We have C alpha 0.002. And then at 10 years from the end of primary consolidation, we have TS over TP around 10, and the log of that is 1. If the thickness is 15 meters, by the way, this side is the thickness of the clay is only 15 meters because there was a 2 meter embankment on top of it. That's why it becomes 17. And if we have 15-meter thickness, we multiply that to the C alpha, 0.002. Then we have 30 millimeters per 10 years. 10 years is TP to TS is 10 years. So the amount of secondary consolidation is 3 millimeters per year because this ground is already over consolidated. The maximum mass pressure increased from 40 to 80 kPa. So now we are dealing with over consolidated soils with low secondary compression. So summary, my summary here, the concepts of PVD and vacuum PVD has been discussed, presented. The vacuum PVD was stopped at the vacuum pressure were discontinued or stopped at 90% degree of consolidation, or the rate of settlement is 5 millimeters per day. The distributed air-water separation device in the field maintained quite efficient and generating a vacuum pressure 80 to 90 kPa. And the CS values, when you have ds over dm equals 2, and ks over ks of 5, or even less, because you have, this is for PVD, but for vacuum PVD will be less, around 4. Then it's provide the CS value for the site. And due to vacuum PVD improvement, the bare soft to soft clay was transformed into soft or medium stiff clay because the water contents, compression indices, void ratios have been reduced, while undrainage strength, OCR, maximum pass pressure, has been increased. The pre-compressed ground would only have secondary compression of 3 millimeters per year. When the vacuum pressure was stopped, the rebound was measured around two weeks afterwards, and it's around 10, at the most 10 centimeters or 100 millimeters. Thank you very much for your attention.
Thank you very much, sir. That is excellent presentation and information that you have. Is there any question? มีคำถามไหมครับ ท่านใดจะถามเปิดไมค์ถามได้เลยนะครับ หรือถ้าไม่สะดวกก็เขียนมาในแชทบ็อกซ์ได้นะครับ Okay, there's a question in the chat box. Okay, the question is, please suggest about the duty or the function of geotextile and geomembrane in the for the vacuum PVD section. I think this may be the function of the geotextile in the VCM, and also the function of geomembrane in the VCM. That's the first question. And the second question is the consolidation time of the vacuum PVD is greater than vacuum PVD greater than PVD for 1.5 times. I think it should be less than. Vacuum PVD should be less than PVD for 1.5 times.
Yes.
Right. How about PVD with preloading? I think PVD with preloading is the PVD. I mean, normally we don't have the PVD alone, right? We just have PVD with preloading, right? Okay. Maybe the second question is the difference between PVD with surcharging or with preloading and comparing with the VCM. What is the time difference? Yeah.
Can you see this slide here?
Yes, yes.
The function of geosynthetics resides in the PBD is composed of geosynthetics. First, we have the geotextile separation below and above the sand blanket. The sand blanket has to be separated from the original ground by geotextile, and then above the sand blanket, you have another geotextile. Then you have the geomembrane, HDPE, for the airtight sheets. This is impermeable membrane. Above it, we have to put geotextile again to protect geomembrane from puncture. So we have 3 layers there now. Below sand blanket, above sand blanket, we have then geomembrane, then above geomembrane, another geotextile. Then that is the function of the geosynthetics here, plus the horizontal strip drain and the vertical PBD. They are all geosynthetics. Then we connect with the tube, and that's the first question.
Yeah.
Of course, the perforated pipe is also wrapped around by geotextile.
Mm-hmm.
The second question about
Timing.
PBD, maybe this one is a good example here. The PBD only, because of the stage loading, you have one stage, second stage. It takes some time to about 1 year in Sonapum, 365 days. Now complete the work. But with vacuum PBD, you can finish at 90% consolidation around 200, a little bit more than 200 days. But now, with the new airtight membranes, we can finish the vacuum PBD in 5 to 6 months. So you compare it with 1 year PBD only, with 5 to 6 months, you reduce by about 50%.
Okay.
The consolidation time, as you can see in our project at this one here, this project, you can see this one, 90%, 200 days is about 6 months here.
Okay.
6 times 30 is 180, 200 days.
The next question is VCM a good method for the land reclamation?
Yes, I think as of now, the cost of the VCM, if you compare the cost of VCM with PBD only, they are almost the same or even cheaper. And because if I look first here, the advantage that given by in my earlier slides, the advantage of using vacuum PBD benefits of vacuum PVD. You can use large preloading and, well, minimize outward movement, and you save time. You minimize lateral outward movement, you save time. And if reclamation, the problem only with vacuum PVD is when there is sand lenses or sand lenses within the soft clay that will affect the vacuum. The effect of vacuum reduced when you have sand in your soft clay layer. You have lenses of sand. But if the reclamation is made of clay fill, or before reclamation, there is a mud below the sea, just improve that one. But if the fill in reclamation is sand, then you cannot use PVD. If it is a hydraulic fill dredge from the sea is made of corals and sand, this one you cannot use PVD, you use only the deep compaction or vibro flotation. You can only use PVD underlying mud below, deposited originally below the sea bed. Is that okay? I cannot hear you.
Oh, I'm sorry. Can you hear me?
Yeah.
Yeah. The next question is, can we use Asaoka method if the vacuum pressure isn't constant?
No, the Asaoka method is working on the settlement. You are looking at the settlement. So if the loading is not constant, then you have to separate your Asaoka method at the different segments of the settlement. So for example, if you have, this one is a settlement here. For example, if your vacuum pressure is not constant, your settlement also is going around. So you can separate the settlement into segments because they are not continuous like that. That make you a lot of headache.
The concept of Asaoka is the prediction have to be based on the constant load that apply. Yeah, basically.
Yeah. So
yeah.
For this load, this is the settlement. Then you can analyze it.
Yeah.
Corresponding to each load.
I see. Okay. There's a few more questions, but I'm afraid that we have not much time left. So let's keep this question until the end of this seminar, and then Professor Bergado, please stick around, and then we might have another round of questions at the end of the presentation. As of now, thank you very much, Professor Bergado.
Okay.
คำถามที่เหลือเดี๋ยวไปถามตอนท้ายนะครับก็เดี๋ยวจะเวลาจะล่วงเลยนะครับผมโน้ตคำถามไว้แล้วนะครับนะฮะโอเคครับก็ในส่วนถัดไปนะครับก็จะเป็น